We're going to look at sketching the graph of a polynomial function, and it could be, this would work for any function, but we're going to sketch the graph of a function, in this case a cubic polynomial. We're going to do that by hand without the use of a graphing calculator, and this is something I'm going to expect you to be able to do on your tests. So the first thing we want to do is think about, our algebra rules and what we know. In this situation, we'll look, does the graph have any asymptotes, vertical or horizontal? This is not rational, so it doesn't have vertical asymptotes. There are also no holes or discontinuities. Something else we might look at would be the symmetry, and I've written some information about symmetry over here on the screen. In order to check symmetry, all you need to do is to plug in negative x. You plug in negative x and you look at the output. Either it is exactly the opposite or it is exactly the same. Exactly opposite gives you an odd function, and you know that that graph is going to have rotational symmetry specifically about the origin. And if it's an even function, it returns the exact same function when you plug in negative x. You would have reflective symmetry across the y-axis. So in this situation, when I go to check that symmetry, I'm going to say f of negative x is negative 2 times negative x cubed plus 6 times negative x squared minus 3. That's negative 2. This is negative x cubed plus 6. That becomes positive x squared minus 3. And you'll notice that only one of the signs change. This first sign changes, but the 6 and the 3 do not change. Since not all of the signs changed or none of the signs changed, we know that this graph has no notable symmetry. So let me erase that. We know there's no notable symmetry. Another thing, and it doesn't say this here on the screen, but is there any information regarding the end behavior of this graph? And by that, I mean we look at that leading term and we consider end behavior. Odd degreed function, odd degree, then we know it is opposite ends. Oops, ends is messy, but we know it has opposite ends. And because it has a negative leading coefficient, we know it is going down, not Dawn, going down. So it's falling from left to right. So that will give us a little bit of information when we think about graphing it, considering that end behavior. All right, and because, if we come over here and think about the domain, there's no symmetry, no asymptotes, no holes. When you think about the domain, it's a polynomial function. So the domain, my x values are between all real numbers. And again, my end behavior, that's some information. We know it's going to be opposite ends falling as we travel across the page. All right, so now let's think about our first and our second derivative. My first derivative, and the derivative of a polynomial is easy to determine. We're going to get negative 6x squared plus 12x minus 0. The derivative of a constant is 0. When we write that derivative, we always want to put that in factored form. So I'm going to factor out, negative 6x, and that leaves me with x minus 2. So if I set this first derivative equal to 0 and solve, I'm going to get two critical numbers. I'm going to get x equals 0 as well as x equals positive 2. So now I'll look at my second derivative. So I'll take that function and differentiate again, and that's going to give me negative 12x plus 12. Of course, we always want our derivative in factored form, so I'm going to factor out negative 12, and that leaves me with x minus 1. Setting the second derivative equal to 0, we're going to get one inflection value, and that's going to be at x equals positive 1. If I tried to set x equals negative 12 equal to 0. Negative 12 can't equal 0. That does not give us an inflection value. So we have two critical numbers and one possible inflection value. All right? We know the domain of our function, and we have an idea of the end behavior. So I'm going to come down here. I'm going to plot these values in my table. I have x equals 0. I should have made this table fit a little better. Let me shrink this a little, because we've got information on the other side of that. All right, we got x equals 0, and then we have x equals 1 and x equals 2. So x equals 1 and x equals 2. I'll just extend this line. We'll know that goes on a little further there. Okay, so those critical numbers, we plot them. And once we've plot those critical numbers on the number line, that lets us divide our number line into intervals. So the left of 0 is negative infinity to 0. And we've got between 0 and 1, between 1 and 2, and to the right of 0 is 2 to positive infinity. Once we have those intervals, we need to choose a test value on each interval. So I'm just going to pick any number. I've got x equals negative 1, x equals between 0 and 1. I have to, unfortunately, pick a fraction. Between 1 and 2, again, I have to pick a fraction, so I'll say 3/2 or 1.5. And then greater than 2, I'll say x equals 3. All right, now, what was my first derivative? It was negative 6x times x minus 2. So I'm going to come over here, negative 6x times x minus 2. That's my first derivative. Now, if the first derivative is positive at this test value, that would imply increasing. And if the first derivative is negative at that test value, that's going to imply decreasing. Now, as we talk about, we don't want to actually evaluate and get more numbers on our paper than we need. We just want to think, is this going to be positive or negative? So I'm going to write some information here. I've got negative 6, negative 1, and negative 1 minus 2. I'm not actually going to calculate this. I'm just going to say, well, negative 6 is negative, times negative 1 is negative, and negative 1 minus 2 is negative. Negative times a negative is positive, and a positive times a negative. The whole output here is a negative value. And that's the easiest way to deal with this without a calculator. So I'm going to erase that so I have more space. And I'm going to say that f prime of negative 1 equals a negative value. And what that negative value implies is that we are decreasing on that interval. So let's look at f prime of 1/2. Now if I come over here and I plug positive 1/2 in right here, that's a negative times a positive, and 1/2 minus 2 will still be negative. So negative times a positive times a negative, that will equal positive, and we know the graph is increasing on this interval. All right, let's look at 3/2. F prime of 3/2. So negative 6 times 3/2 will still be a negative number. 3/2 take away 2, 1.5 take away 2 is still a negative number, and a negative times a negative is positive, increasing. Last piece here, f prime of 3. Negative 6 times 3 is a negative number. And then 3 minus 2, that's positive. So negative times a positive will remain negative. Our graph is decreasing. So we are decreasing from negative infinity to 0, and we are also decreasing from 2 to positive infinity. And then we are increasing between 0 and 2. Now, where we change from increasing to decreasing, or decreasing to increasing, represents a max or a min. So we're going down and then we go back up we're going to have a min at x equals 0. And then over here at 2, when we're going up and then we change to going down, that's going to represent a max at x equals 2. All right, now let's talk about our second derivative here. Our second derivative we said was negative 12 times x minus 1. So we're going to employ that same positive negative logic. So f double prime of negative 1. Well, it's always going to be a negative 12 in front, right? A negative in front. This guy is always going to be negative 12. What is negative 1 minus 1? That is still, that's still negative. So negative 12 times negative 2, we're going to get a positive value here. That indicates that we have concave up. Now, keeping in mind we have concave up included on this decreasing interval, we're only going to have the left half of our concave up curve. All right, we'll do that again. F double prime of 1/2. So negative number in the front. What happens when we have 1/2 minus 1? That's still negative. 0.5 minus 1. A negative times a negative is positive. So again, this is concave up. But on this concave up interval, we are increasing. So concave up increasing is the right half of our concave up curve. All right, let's pick another color here. So lastly, we've got two more curves to deal with, or two more sections of our interval. F double prime of 3/2. So when I plug that in, negative 12 is still in front. 3/2 take away 1 is positive, and a negative times a positive is negative. So that indicates concave down. Concave down increasing is left half of our concave down curve. Let's look at one more. F double prime of test value 3. Negative 12 in front. 3 minus 2 is positive. Negative times a positive is negative. So this is concave down, and it's concave down decreasing. All right? So again, when you are drawing these sketches, don't draw a U or a frown. Draw the left or the right half. That's what's going to help you interpret your information. All right, so let me pull these up here so we can talk about what our conclusions are going to be. All right, so what interval is this function increasing? We are increasing, those blue lines go away. We are increasing all in this range. So our increasing graph is increasing interval is 0 to 2. And our decreasing intervals are to the left of 0 and the right of 2. So that would be negative infinity to 0 union. That would be 2 to positive infinity. And we also said we would have a max or a min. Now the max or the min is an ordered pair, and that ordered pair comes from the function. So my maximum is occurring at x equals 2, and my minimum, we said, was occurring at x equals 0. We'll talk about finding those points in a second on the next page. I'm going to go ahead and open up my calculator so it's ready. All right. Concave up intervals. Oh, I don't have enough space for all that. Let me just this and shrink it down just a little so I have space to write on the other side. All right, so where's the graph concave up? We are concave up from negative infinity to positive 1, all in this region were we concave up, negative infinity to positive 1. And we're concave down on the other side of that, concave down from 1 to positive infinity. So all over here was concave down. And where the concavity changed, right in between those two, here is where we had our inflection value. Our inflection value was at x equals 1. All right? So now that we've, determined all this information, let's take this to the next screen and we can graph this. So I'll come over here, or maybe I put it down. I think it scrolled down. All right, so here's our graph. Now we had some points of note. We had x equals 0, we had x equals 1, and x equals 2. If I want to know what those points are on the graph, I'm going to go to my graphing calculator and type my function in, negative 2x cubed plus 6x squared minus 3. Negative 2x to the third plus 6x squared minus 3. I'm just going to use my calculator here. We can plug and chug without a calculator, but this is going to speed up my work. I know I said this was a no calculator problem. All right, but plugging those points into the calculator, negative 2x cubed plus 6x squared minus 3, what I'll do is I'll go to my table and I'll look at what my outputs are. At 0, I get that point negative 3. At 1, I get positive 1, and at 2, I get 5. So it's just a matter of plug and chug. What did I say? I said negative 3, 1, and 5. So negative 3, 1, and 5, those represent the ordered pairs on my graph. So I'm just going to sketch this. I've got 0, down 3. I have over positive 1, up 1. And then I have right 2, up 5. So over 2, up 5. And you don't have to make your y-axis to scale. Sometimes it's easier if we don't have it to scale. All right? So and what I mean by that is I'm just going to say, all right, 0, down 3, this is down 3, over 1, up 1, and over 2, up 5. That is just higher. It doesn't matter. So 0, negative 3, 1, 1, and 2, 5. Those are my points on my graph. All right, now, did we say anything about the end behavior going all the way back to the top? We said the end behavior, we were going to be rising and then falling. So we do know that the ends start high and end low. And we're going to try graphing this from the left to the right as we travel along the page. So what did we say was happening to the left of x equals 0? So I'm going to scroll back up here. To the left of x equals 0 on our table, we said it was concave up. We hit a minimum at 0, and then we were still concave up until we went to 1. So scrolling back down. We are concave up decreasing, and at 0 we switch to concave up increasing. Now, when we get to 1, that was another value where things changed. So at x equals 1, to the right of that, we became increasing concave down. So what does increasing concave down look like? Sort of like that. And then at x equals 2, once we moved beyond that, we were decreasing concave down. So the graph goes down like this. And that is the general idea of how we graph this curve. We want to make it a smooth line when we draw. It doesn't have to be perfect, but it does need to be smooth, no sharp points, because that would mean we have a value which is not differentiable. So I know this was a long video, but this is a long process. I can't cut it down any shorter. I really want you to be able to hear what I'm talking about and what I'm thinking about when we look at these problems. And you are going to be expected to do something like this on your test, to be able to tell me all of those different values, especially if we are in an in-class version. Do all of this interpretation without a calculator. And it's really going to benefit you once you get into Calc 2 or Calc 3 later, if you have a good understanding of what these curves look like. All right, so making the table is important, and I want you to have that skill. Please let me know if you have any questions or concerns. I am here to help.